All right, welcome to our next lecture here in 1.5, where we're going to take, in 1.4, we looked at the family of functions that are kind of common and what their basic sort of most simplest graph looks like. And I talked about how we're going to learn how things that we do to those graphs or to those equations, we're going to look at how it affects their graphs. And of course, the graphs are just a reflection of the set of ordered pairs that make any particular equation or function true, right? It's the pairing of an x and a y that make the left-hand side equal to the right-hand side. So with each function we look at, we want to think about, all right, what is the core function that this particular function we're looking at, where does it come from? What is the core graph and function, what do they look like? And then we're going to then examine what has been done to this function from its original form. And then from that, we can look at some patterns that develop that can give us clues and can actually aid us in graphing these functions. So if a new function is formed by performing certain operations, and we talk about operations, of course, we're talking about adding, subtracting, multiplying, dividing. So we take our original function and we add things to it, subtract things from it in various places of the function. What that does is it gives us a new function, and then the graph of that new function we say is a transformation of the original function f. All right, so let's look at some examples and graph these side by side. And we'll start off with one of the graphs that we looked at in our family of functions, which is the absolute value function, f of x equal to the absolute value of x, which the absolute value of x, of course, simply is a measure of the distance any number is from 0 on the number line. That's the definition of absolute value. So I've got some prepared numbers here, and we're going to look at how these change by when I add 2 on the outside of the f of x, and then when I subtract numbers to the outside of the absolute value of x. All right, so let's start off with just the original formula, f of x equals the absolute value of x. When I substitute the negative 4 into that, very simply, that negative 4 becomes positive 4. And so the result is positive 4. Let's change the color. That's a little bit hard to see. And plugging in negative 2, of course, the distance of negative 2 from 0 on the number line is also 2. Then we have 0 just is 0 units from 0 on the number line. And then 2 and 4. Okay. And we've kind of already seen this before. We know 2 gives me 2, 4 gives me 4, negative 2 gives me positive 2, and negative 4 gives me positive 4. And so using a hard edge to graph these lines, we can graph the equation. Okay, let's go to the next one now. Remember, now g of x, we're just using a different letter there, but when we look at the absolute value of x within this equation, remember, compared to the original, that's basically my outcome, right? And the outcome, g of x, is just my f of x, right? And f of x represents the y. This is my list of y outcomes, right? This is my y being equal to the absolute value of x. So in other words, for this first one, that negative 4, positive 4 was the y outcome of substituting negative 4. So when we're adding 2 to that, we're really saying, okay, the outcome is going to be increased by 2. The y outcome is going to be increased by 2. So we can see that, right, when I go g negative 4, I get absolute value of negative 4 plus 2. Well, the absolute value of negative 4 is 4. And so what happens is I'm just going to add 2 to the original outcome I had here in this column, right, in the f of x, the original column. So that kind of helps me here. I see if my outcome was 4, that means I'm going to add 2 to that, so my outcome would be 6. If the outcome here was 2, I'm going to add 2 to that. That gives me 4. 0 plus 2 is 2. 2 plus 2 is 4. And 4 plus 2 is 6. Okay. So plotting out these points, I'm going to use a different color here. We're at 0, 2 now. Notice that 0, 2 is kind of my lowest point on the graph. We can kind of call that, it's not really a vertex, but I'd say it's the lowest point on my graph, which is kind of important idea there. And then 2 gave me 4, 4 gave me 6, negative 2 gave me 4, and negative 4 gave me 6. Using my straight edge, we plot it out, connect the dots, and there's our graph for the other one. So what we see here is that my graph has shifted up 2 units for each point. 0 to 2, oops. There we go. We went from 0 to 2 and then 2 to 4 on down the line here. So the whole graph basically just moved up. It's got the same angle to the axes and everything. It's just been moved at. So for going to the last one here, again, it's the same idea. We've got h, and then we're subtracting 3. So for every y outcome in my original column over here, I'm going to subtract 3 for each one. And so 0 minus 3 is negative 3, 2 minus 3 is negative 1, and positive 2, negative 1, and then 4 minus 3 is 1 for each of those. So let's go ahead and plot those out. 0 minus 3, then we have 2 and negative 1, negative 2, negative 1, and then 4, positive 1, negative 4, positive 1. Using a straight edge, we're going to graph those out. And there we have the graph of h of x. Notice that from my original equation, each point has simply moved down 3 units from the original graph, from the f of x. And that was because I subtracted 3. So by subtracting 3 to basically the equation of f of x, absolute value of x, the only change that resulted really was that it moved up and down, and it moved up and down the number of units I was subtracting or adding to. So we can make some general things here. Again, this is one of those wordy kind of mathy things, but let's go through this and kind of parse it out a little bit. It's really important to challenge yourself a bit here in trying to read through this. Sometimes as you're learning how to read through mathematical language, you might have to go back and kind of reread some parts, look at what it means on the graph, graphically. So at any rate, we say, let's assume D is a positive number. Then the graph g of x, where we take the original f of x, right? Our f of x was like that absolute value of x, and we add something to it, is the same as the graph, or is the graph of y equal to f of x shifted d units up. And then the graph h of x, when we subtract it, is the same graph, f of x, shifted down d units. So if xy is a point on the graph of f of x, then the corresponding point x, y plus d is on the graph of y equal to f of x plus d, right? When we added it, we basically added d to all the y values, shifting them up. And the point x, y minus d is on the graph of y of f of x minus d. So we see that here. Here's our original graph, whatever it is, f of x. And we see it shifting down. So we took that, and here we see it shifting up, right? Same shape, just moved and sort of transformed up or down depending on whether we were adding or subtracting. So, what we saw in the previous slide was for a very specific function, the absolute value of x. But here what we are is we're generalizing that experience to any function f of x. If we are adding something to the basic equation that makes up our family of equations, the outcome of that addition or subtraction, is that it shifts it up or down that many units. All right, now let's look at a different sort of example, and we're going to start off with the basic equation f of x equal to x squared, which of course is a quadratic, a squared type of equation. And I want to just go ahead and fill in some points there and plot that out first. So if I take -2 and we plug in -2, and we're doing that in the parenthesis there, and we're squaring that, we see the square of -2 is going to get rid of the negative. So just like with the absolute value, it becomes positive. And then we have the square of -2, which is 4. Doing the same thing with -1, the square of -1 is going to be just +1. And of course, the square of 0 would be 0. If it's a +1 and I square it, there's no real difference in the outcome there, and we can assume that's also going to happen with 4. +2 squared is +4. So here's the basic pattern that we've established, and this kind of confirms what we suspected would be the case. Let's see, -1 is 1, -2 is 4. And we've seen in our family of functions what the squared, x squared equations look like. They give us this parabola, and there we have it. Okay. Now let's talk about doing stuff with this, but as opposed to what we had in the previous, we're going to not subtract 2 to x squared, but instead subtract the 2 from x before we square it. So in essence, what we're subtracting from in this case is the input. We're subtracting 2 from the input of x before it's squared. So really the action is happening not to the y, to the result of, right, this would be the y, the x squared. That's the real thing. When we square it, that's when it really takes on the qualities of the parabola. But instead, so we're not subtracting from that, the y, we're really subtracting from the input before it's squared. All right, so as we look at that, how does that affect our graph? If I plug in -2, oops, I just kind of mess with the whole thing there. So I take the g of -2. So substituting that in there, that gives me -2 minus 2 squared. Well, -2 minus 2 is the same as -2 plus -2. And so we see -2 plus -2 is -4. -4 squared is positive 16. So this gives me positive 16. And then let's move to the next one. So very different outcome there than what we had before. -2 minus 1 is -3. So that's plus -1. And -3 squared is 9. And then 0 minus 2. So, whoops, let's undo that. Sorry for the awkward pause there. I was looking at my numbers and I realized I had done something wrong there. It doesn't result in anything different, but the subtraction of it should have been -1 minus 2, not -2 minus 1. I erased the wrong number. But that still gives me -3 squared, which is 9. And so if we move on again with 0, so the g of, I'm just not even going to write the g of 0 anymore. Let's just do the other part of it. Let's just plug that in there. So we have 0 minus 2 squared, and that's -2 squared, which is 4. And then the next one we have there is 1. So 1 minus 2 squared, well, that's -1 squared, which -1 squared is 1. And if I have a 2 there, 2 minus 2 is 0, so that gives me 0 squared. All right. I'm just going to plot some of these out. Some of them I can't really plot because they're off the charts. But we saw at 2 now we're at 0. At 1, we're at 1, so we actually have a similar thing there. At 0, we're at 4. And then at -1, we're at 9, which 6, 7 would be 8, 9 would be way up here. Notice what has kind of happened here. And then it continues to go higher, right? We go to -2 and we're at 16. You can kind of see there that if I plugged in some more points here, like let's say 3 and 4, 3 minus 2 is 1, and 1 squared is 1. And 4 minus 2 is 2, and 2 squared is 4. So we start to see that this is also a parabola, but we've shifted where its vertex is, which is the lowest point there, over. 3 gives us 1, 4 gives us 4. So in an interesting way, when we did something to the x before it was squared, it also shifted it, but it shifted it horizontally. And notice that it shifted it in the opposite direction that we would expect. It shifted it to the right 2 units. And that's when we subtracted 2. Right? We subtracted 2 and it shifted it to the right 2. Interesting. And so we'll take note of that. Now let's go on to the next one. We're going to look at h of x, which is the addition of 3. So plus 3 and squared. And we'll start with our -2. Well, -2 plus 3 is 1, and 1 squared is 1. And, okay, now let's go to the next number there, which would be -1. And -1 plus 3 is 2, and 2 squared is 4. And then we can look at 0. 0 plus 3 is 3, and 3 squared is 9. And following that same pattern, 1 plus 3 is 4, 4 squared is 16, which is way off the charts. And 2 plus 3 is going to give me 5. 5 squared is 25. Oh, dear. So I'm going to put this into another color here. Let's just graph what we have. -2 gave us 1. -1 gave us 4. And then we can't really graph beyond that. Go up to 9 kind of up here. So my guess is -3 here. If I go ahead and plug that in, -3 plus 3 is 0, and 0 squared is 0. What do you think -4 is going to be? Well, -4 plus 3 is -1. -1 squared is 1. So -3, 0, -4, 1. We can guess -5 here would be at 4. And -5 plus 3 is -2, which -2 squared is 4. All right. So what we see kind of roughly here is that when we added 3, it shifted, and we added 3 not to f of x. Remember, we're adding it to x before we square it. And what we're seeing with that is that it shifts it in a horizontal way, and it shifts it in the opposite direction depending on what we're doing. If we're subtracting, it's actually shifting it to the right, and if we're adding, it's shifting it to the left. So let's look at some generalizations of the pattern that we're seeing there. I'm going to write this here because I didn't like the way that so if we have f of x as our first equation, f of x minus c shifts 3 to the right, or c to the right, not 3. Sorry, we did move 3. But, and if we have if we start out with the f of x, and we have an f of x plus c, we saw that it shifted c units to the left. So what we see is opposite direction of the sign. All right, let's combine these together, some vertical and horizontal shifts. And we'll start off with x here. And this time we're looking at the f of x of the square root of x. I'm going to start off with 0. We know with square roots we can't go negative, so I'm going to do 0, 1, and 4. And we can kind of look at the pattern that we see there. So the square root of 0 is 0, and the square root of 1 is 1, and the square root of 4 is 2. If I were to take it out one more, let's say I would need to go to a perfect square, but let's go ahead and take it to 6, and we'll get a decimal. What is the square root of 6? Well, the square root of 6 is a decimal, so we're just going to approximate it a little bit. And we see that it's about 2.5 approximately. So about 2.5. I'm going to use these to plot this out. This gives us enough to kind of go with here. We see 0, 0, 1, 1, and then 4, 2, and then 6, 2.5. And so what we see is this sort of, it's almost a sideways half of a parabola going. It's increasing, but then it's decreasing in its acceleration. It's decreasing in how quickly it's going up. To get to go another half of a unit there, we'd have to go out to 9 before we get to 3. Okay, so that's what we have here. That's the basic graph. Now let's look at it from a standpoint of transformation. And real quickly, I'm going to go back to our previous slide. One of the key parts of the parabola that we can look at is the vertex. When we're graphing it, we know, like for this graph, we have the lowest point here. For the V, you have that point where the two lines come together, kind of a vertex as well. The shifting of that vertex is really what we can use as our base. Because notice that here with the vertex at 0, 0, on either side of that vertex, we had the matching numbers, right? Here, my vertex was at 2, 0, but then we saw that symmetry around that here. And the same thing was true here, but it's harder because of the way I wrote it to see that. But if we can establish that, then we can sort of go to the left and to the right of that vertex and know that the outcome is going to be similar. If I go 2 to the right, we're going to go up to here, and 2 to the left, we go up to here. So we have that symmetry. So the first thing as I look at this graph that I want to kind of establish is where the beginning point is, right? This is kind of the start of this graph. And let's look at the transformation. So at any rate, we've added 2 to the x before we've taken the square root of it. And so we know that this is it's been shifted 2 units, and since we're adding the 2 and it's with the x, we know it's going to be opposite, so we're going to say to the left. So we shifted 2 units to the left, and then the subtraction of 3, notice, happens on the outside of the radical. And so we know and we saw that the way this affects it is that it's going to shift it downward, because with the vertical shift, the vertical transformation, it followed the sign, right? So when we subtracted 3, it went down 3, and so this would also shift 3 units down. So from here, I know I'm going to shift 2 units to the left. I'm just going to draw that down. And then 3 units down. So my suspicion is my first point there is going to start at -2, -3. So our new sort of starting point there is 2 units back and then 3 units down, so at -2, -3. And we can actually see that over here. When we do the substitution, if we go g of -2, that gives me square root of -2 plus 2 minus 3. Well, -2 plus 2, we know that becomes 0, and 0 minus 3 is -3. So our suspicion is correct. That's going to be my new starting point. And as I'm planning this out, I'm going to try to plot points in a similar pattern to what we had before. And in this, I have one number that's kind of left out here. Let's look at where this point here would be. If I go back 2, that puts me at -1, and then down 3, that should take me down to -2, -1, -2. And so I suspect that I'm going to get -2 here. Let's check it out and see if my suspicions are correct. So we're going to plug in -1. So that's -1 plus 2, square rooted, subtracting 3. -1 plus 2 is a square root of 1. And 1 minus 3 is equal to -2. So just like we suspected, -1 gave me -2, which is what we have here. The next point was at 4. If we took 4 back, 2, and then down 3, I suspect it would put me here at 2, -1. Plugging these in, we can get an idea if that works, if g of 2. So by establishing our starting point here, the -2, that kind of can guide me on what values I want to plug in here. I'm just trying to find the same pattern. 0 to 1, well, if I started out at -2 and moved to the right one, I'm at -1. So -1 becomes my next point to plot. Now I'm going to plot 2, square root of 2 plus 2, and then minus 3. 2 plus 2 is 4. 4 minus 3 gives me 2 minus 3, which is -1. And that's where this point is. Following that same pattern, just like we thought, it's kind of creeping through there. And I put in 7 because we can afford to plug in some higher numbers here. And looking at the equation, I know that 7 plus 2 gives me a perfect square of 9. So 7 plus 2, and square root of 9 is 3. 3 minus 3 is 0. So 7 and 0 would be right there. So at any rate, here's the graph of this function. We can see that every point along the lines here is a combination of shifting the original points back 2, and then down 3. So what we saw, and just to kind of summarize what we saw here, is that with any equation, starting it out from its sort of fundamental equation, the father equation, if you will, when I add something on the inside, when I add something to the x, if we add or subtract to the x, so we add or subtract to the input, it moves horizontally in the opposite direction. So if we add, we're moving to the left. If we subtract, we're moving to the right. And if we add or subtract on the outside, so we're adding to the y, it moves it up or down in the same direction. Up or down in the same direction as the operation. All right. I've kind of modified this a little bit from the original intent of it because I wanted to maybe give you an example before we get into the theoretical here. But we're talking about the reflection about the x-axis. And when that happens, when do we see a graph reflect itself around the x-axis? We did talk about the reflection around the y-axis, but we haven't really talked about a reflection across the x-axis. And basically it happens when we multiply by a -1. We take our original fraction and we multiply it by -1. So I want to start off over down here. So I'm going to divert your eyes down in this direction. And then we'll go back up to the rest there. So I wanted to start with an equation here, f of x equaling the absolute value of x, which we already know what that looks like. And then I want to graph a second equation, which we'll call g of x, which is going to be the opposite of f of x. Well, if f of x is the absolute value of x, and I want to basically take the opposite or multiply it by -1, that would just put a -1 or a negative in front of the function absolute value of x. And plotting out some points, we know that this gives us a v, so plugging in, for example, 0 just gives me the absolute value of 0. Plugging in 2 will give me 2, and plugging in -2, the absolute value of -2 is also 2. And we get 4, and same thing here, 4. So graphing this out, we have our 0, then we have 2, 2, -2, 2, and then 4, 4, -4, 4. And then using our straight edge, we can graph that out, and we have the v, which is what we expected based on our previous experience. All right, now graphing out my g of x, notice that really this negative here in front of the x squared just is going to negate everything in the f of x column. So whatever my outcomes were, whatever my y values were, they just become the opposite of what they were before. So +4 becomes -4, +2, -2, 0. Well, there is no positive or negative with 0. And then -2 again, -4. Right, so I'm taking the y outcomes and I'm reversing them. And so putting those into graphic form, that's 2, +2 for x, -2, -2 for x, -2. And then +4, -4, +4, -4, or -4, -4. And connecting my dots here, using a straight edge, we have our graph. So every point that was above is now beneath. So for +4 becomes still +4, but now my y is just the opposite, which makes sense because we took the opposite of the y. Remember, f of x represents the outcome, represents the y. And so we just took that outcome, which was the absolute value of x, and we took the opposite sign. So it doesn't mean everything's going to be negative. It just means everything will be the opposite of what it was before. So going back to the definition here, g of x equaling the opposite of f of x is a reflection of the graph of f of x about or across the x-axis. So if we have a point xy that's on the graph of f, then the point x negative y would be on the graph of the g. We can see that here. Here's a xy point, moves down here with the opposite. But I also want to point out that over here, if we take this graph and it's down below, the g moves it up above. So a lot of times when we see negatives in front of variables, we want to think opposite, because it doesn't necessarily mean that the outcome is always negative. It just means that the outcome is going to be opposite, because the negative of a negative is a positive. So just keep that in mind. And let's talk about now the reflection across the y-axis, which we saw earlier was an even function. But we're going to look at it from a slightly different perspective here, where we start off with f of x, and then we change the equation slightly by inserting a negative in for x, which takes a little bit of us, we have to look at it differently. Let's just start off with something more familiar. So I wanted to start again with an example over here. And we're going to take the square root of x as our example, something we've worked on just a couple slides ago. And I'm just going to go ahead and graph that. We saw, of course, this has a domain, and the domain of this is going from 0, including 0, all the way up to positive infinity. And so we'll start with 0, then I'm going to use 1, and then 4. Those are our kind of nice numbers that we can use there. The square root of 0 is 0, square root of 1 is 1, and the square root of 4 was 2. So that gives us enough points here to give us a graph. And we saw kind of how this behaved. It's kind of a gradual, like a sideways parabola here, but only half of it. All right. So with g of x, we're going to define g of x as being f of the opposite values of x. And that, if I put a negative in with the x, that gives me a negative square root of x. Now, I know how we talked about how we can't have negative number outcomes underneath the radical. And so by me inserting this negative here, some of you might go, well, you can't do that. Well, yes, we can, because we're putting it in front of a variable, and a variable, we can plug in anything we want for a variable as long as the result is not something negative, right? What that negative does for our domain is it actually, the domain of this function is now the opposite of what it was before. I can have a negative there, but that changes what I'm allowed to plug in there. Because that we know, like, for example, let's just take a negative number like negative 1. The negative of negative 1 is actually positive 1. And so as long as my domain is made up of 0 or negative numbers, then I'm allowed to plug it in. So my new domain then goes from negative infinity, every negative number, all the way up to 0, including 0, because, and now I'm getting into my graph there, but so I'm going to move that if I can. Let's see if I can get that moved over here out of my way. There we go. This is the domain here. It now is the set of all negative numbers. So by doing the putting a negative with the x, right? I'm not making it the negative square root, but rather the square root of the opposite values of x, so the opposite domain. I've changed the values that I'm allowed to plug into. So I can't even use the same set of values here. I would have to use the opposite of those values, 0 -1 and -2. But as we saw when we plugged in 0, of course, the square root of -0 is the same as +0. When I plugged in the -1, we saw that that becomes the square root of the negative of -1, or the opposite of -1. And it helps sometimes to think of negative, especially when it's in front of variables, as being opposite. So that gives me the square root of +1, which is 1. So for the g of x function, -1 gives me 1. And the negative of 2 is going to give me positive. Oops, I didn't want 2. Sorry. I meant to put 4. The opposite of what I had over here. So we'll put -4 there. -4, the opposite of -4 is +4, and the positive square root of +4 is 2. So we kind of did a trick there. We took the opposite domain, but when we took the opposite domain by putting a negative with the x on the inside, it gave us the same y output. We ended up having to plug in the opposite values to counteract that negative that we put in there. But that gives us this. So we end up with 0, 0, -1, 1, and then -4, 2. And you can see the graph that we got here is reflected across the y-axis rather than the x-axis in that case. So now let's go up to the theoretical of what we just did. The graph of g of x, if it involves us taking the opposite domain, would be a reflection of the graph of our original graph across the y-axis. So think of that negative x as being the opposite domain that the original f of x function had. In other words, if the original f of x function was made up of negative numbers, then the domain in the f of negative x would be made up of all the opposite of the negative numbers, so the positive numbers. So again, when you see negatives with variables, it helps to substitute that word in your mind, opposite. So if a point xy is on the graph of f, then the point -xy, the opposite domain, will still give us the same y on the graph of g. And we see this over here. We've got our graph here. One of the things is xy. And so if I know that fxy is on this graph, and this graph here is really just made up of the opposite domain, -x would give me y over here. All right, so let's look at another example now that we have that of if we have a graph that starts off as y equal to the absolute value of x. If I have the absolute value of x minus 2 and then plus 3, what kind of transformation I'm going to see there. And then let's throw in a negative in front of that absolute value. That, of course, will reflect it, and it's in front of the absolute value, right? It's the negative of this. What that tells me is it's going to be reflected across the x-axis. All right, so let's just run some numbers here. And first thing I would like to point out here is let's think about the transformations, because we know that absolute value of x gives me that v that looks like 4 and 4, 6 and 6, -2, 2, -4, 4, -6, 6. Bada bing, bada boom. There we have our graph of y equal to the absolute value of x. So again, I want you to think about the low point here. And it's kind of like us looking at that starting point for the square root function, also like the vertex of the parabola function. I want to think about what we've looked at as far as the shifting is concerned. So I'm just going to look at what we're adding and subtracting. When we add and subtract things, it shifts the points in those directions. The subtraction of 2 shifted my graph horizontally in the opposite direction. So this would be shifting it positive 2 to the right. And then the adding of 3 is to the outside of the absolute value functions. And what we saw with that is that it shifted up 3 units. So it went in the same direction. So if I'm going to begin to figure out where this sort of starting point is, which will give me an idea of what x values to plug in over here, I want to take my low point here and do those shifts. So if I go 2 to the right, and then I go up 3 units, we see that my beginning point here is at 2, 3. So that gives me 2 as kind of a point I'm going to just put in the middle. Because what I'm going to do from now is I'm going to plug a couple points to the left of it, a couple points to the right of it. So in other words, if I go a couple points to the left, that would give me 0 as an input. So I'm going to use 0 here. That's to the left. And if I go a couple points more to the left, that would put me at -2. So I'm also going to plug in -2. And if I go a couple points to the right, that has me at +4. I'm going to plug in 4. And then a couple more to the right, that's going to put me at 6. All right. So notice that I'm expecting, number one, for 2, 3 to be my new sort of point of the V, right? So let's go ahead and plug that in there. F of 2, I'm sorry, yeah, this is F. So F of 2, if I plug 2 in there, that's the negative absolute value of 2 minus 2, and then plus 3. Well, 2 minus 2 is 0, so that's the absolute value, the negative absolute value of 0, which is still 0, plus 3. So we see 2, 3, indeed, is the sort of V point on my graph. Now let's go with 0, right? I found that point, and now from 2, 3, I want to use that kind of as my point where I decide where I'm going to plug things, or what values I'm going to input over here. Otherwise, you can end up getting really big, crazy points that are way off your graph. But if we stay within the general vicinity, kind of like we did here with the original graph, in other words, we don't, I plugged in 2, and I got 2, and I plugged in 4, and I got 4, and I plugged in -2, and then I plugged in, and so I stayed within that general vicinity of 0, 0. But when I've shifted it and moved it, I need to do kind of the same thing. So I went 2 to the left, 2 to the left, so I subtracted 2, and then I went 2 to the right, 2 to the right. Now, that doesn't mean that you always want to choose 2. Sometimes, like with a parabola, it gets really big really fast, so you probably just want to subtract 1, add 1, add 1. So you depending on the type of equation, if you have an idea of what you're doing to it, you can kind of control the output here. This is what we're trying to control. Is we don't want to get crazy numbers. Like you saw, I was getting 16 on that one graph, right? This is going to prevent that from happening. All right, so let's go with f of 0. And the f of 0, that gives me the negative absolute value of 0 minus 2, and then plus 3. Well, that's -2, but the absolute value of -2 is 2. But then notice this little negative on the outside, that keeps this negative. So it came out positive, but then this little guy that's on the outside of the absolute value made it negative again. Surprise, surprise. And so we get -2 plus 3, which is 1. So 0 gave me 1. I can assume this also is going to give me 1. Why? Because it's the same distance away from that point, but let's make sure. This would be the f of 4. So that would be 4 minus 2, absolute value. Well, 4 minus 2 is positive 2, but again, this negative comes down, so it makes it negative 2 again, and negative 2 plus 3 is 1. So you can see that pattern there. Once we've established the pattern and we keep it going, if I go ahead and plug in the next number, which is negative 2, so we have the f of negative 2, and we know that's the negative absolute value of negative 2 minus 2 plus 3. Well, negative 2 minus 2 is the same as plus negative 2, so that's negative 4. And the absolute value of negative 4 is positive 4. But again, this negative is still on the outside there. It's going to attach to it. Negative 4 plus 3 is negative 1. So I can assume this will also be negative 1. All right. So that's the benefit there. We don't have to plug in all the numbers. Once we've established, you do want to establish it and make sure that you pick the right points there. You're not making any mistakes. Once you've established that both this and that, then if we followed the pattern, I don't really need to plug in the last number here. You can eye it, but 6 minus 2 is 4. That's positive 4, and the same thing happens. Let's go ahead and plot these points, though. We're going to keep this one in red. So negative 2, so 1, 2, gave me negative 1. That's down here. And also, what else gave me negative 1 was 6. 6 also gave me negative 1. Interesting. We plotted out 2, 3. So here we have 0 and 1. So that would be right here. And 4 and 1. Connecting the dots here, we can see the effect of that negative. The negative in front of the absolute value sign basically flipped the original equation upside down. So if you can visualize here, I'm just kind of eyeing it. I'm not actually doing it here. But that negative basically took my original equation, flipped it upside down, and then shifted the additions and subtractions, shifted it and moved it up 3, and then to the right 2. So the negative, whenever we have that, it's reflecting it across the x-axis here to the original function. And then the adding and the subtracting, both the adding to the y, shifting it up, and then the subtracting with the x, shifting it. When I was subtracting it, it shifted it to the right. If I was adding to the x, I would move it to the left. But it basically shifted that upside down v to a new vertex spot. Right? So our exploration here kind of gave us our strategy as well. Knowing that we have these shifts, and then knowing the effect of the negative, like if we have a negative in front of an x squared, that's going to flip our regular parabola that's going up. It's going to flip it upside down, and then whatever I'm adding and subtracting, either inside with the x or on the outside to the x squared, it's going to shift that upside down parabola in different directions. We can also think of just, negating something, right? Putting a negative there. We can see that as a multiplying by negative 1. 1, of course, doesn't change the value, but the negative 1 part would. So if I was multiplying by positive 1, that wouldn't change anything. But since I'm multiplying by negative 1, that made everything the opposite of what it was originally. All right, let's explore that whole multiplication thing a little bit more. we're going to look at taking an original equation here, f of x equaling the absolute value of x, and here we're taking the absolute value of x, multiplying it by 2, and then here we're going to multiply it by a half. We're going to sketch these three on the same plane and see what happens. So we know already the f of x, right? And these, notice that this is a little bit of opposite of what we've done in the past. Here are the x values that we're inputting. We're going to input the same x values every time. So I'm just going to highlight those in blue so we can kind of see that these are my inputs, right? And then I'll use other colors for each of these. Let's just start out with the basic of the absolute value of x. We kind of already know that. We just saw it on the previous slide. Positive 2 will give me 2, positive 4 will give me 4, positive 6 will give me 6. And same on the other side. And no big surprise here. There's our v that we got. Negative 2 gave us positive 2, negative 1 gave us positive 1, 0 gave me 0, 1 gave me 1, 2 gave me 2, and then we have the 3 and the 4s and the so forths. Okay, so what about g of x here when I do that? When I multiply the absolute value of x, so the result that I got here, and I multiply it by 2. I don't even really need, since I have the results of f of x, I can just take each one of these results and multiply it by 2. So 2 times, my result of 2 multiplied by 2 is 4. My result, right, f of x is the y. The result of negative 1 was 1, so that result gets multiplied by 2, so we have 2. And we see that here and here as well. So in other words, remember, g of x is twice f of x. F of x was the absolute value of x. So let me write that out. G of x was twice f of x. Because remember what f of x was? Well, f of x was the absolute value of x. So I took that result, the absolute value of x, and I multiplied each of those by 2. Plotting those out, and let's put those in red, because that's the color I'm going to use here. We see 0, 0, so the same starting point. Negative 2 is giving me 4, and positive 2 is giving me 4. Yep, and then negative 1 was giving me now 2, positive 1, 2. And so the pattern here that we've seen, we didn't shift our thing anyway, because notice that in this graph there wasn't anything added or subtracted to it, but we multiplied instead. I didn't quite get that on the mark, but I'm pretty darn close. Using my straight edge here. So it didn't shift at all. What it did is it kept it in the same spot, but it kind of stretched it upward. And it stretched it according to the y. It took this value here and actually doubled it. So we're at 2, now we're at 4. Here we were at 1, now we're at 2. And so my y values doubled in size, but they stayed anchored in the same spot. Again, that vertex there for that v remained consistent. It remained in the same spot. That's why we have 0 here for each time, because if I plug in 0, any multiplication is still 0. Okay. Now let's go to h of x. H of x is similar, but we're multiplying it by a half. So again, thinking in terms of f of x, 1/2 of absolute value is the same as 1/2 of f of x. So half of 2 is 1. Half of 1 is a half. 1/2 times 1, 1/2. 1/2 times 2, 1. We're going to go ahead, and I should have just done this in the first place. I keep on forgetting to change my colors. So 0, 0, 2, 1, oh, I'm sorry. positive 1, 1/2, 2, 1, negative 1, or positive 1/2, negative 2, positive 1/2. If I put in 4, absolute value of 4, this would half the original amount of 4, so 4, 2, negative 4, 2 also. And I'm just putting those there because for my drawing's sake, and these are pretty simple calculations. Just whenever I add another, if I want to draw something, it helps to have them kind of spread out. So we see that when we multiplied by 1/2, it actually compressed it. It took every point of my original one and cut it in half, which made it a sort of, if you can think of as pushing down, kind of compressing the original function absolute value of f, or the original function f of x. So when we multiply by a value that is greater than 1, like a 2, we see it stretched upward. And if we multiply by a value that's a fraction, we see it sort of compressed vertically. So smushed a little bit, if you will. We can kind of just give a description of this. We see the graph g of x. If the graph of g of x is a times our original graph, think of f of x as our original graph, is obtained from the graph of my original graph being f of x. So my g of x graph is a product of my original times something. A we think of as some sort of number. So we're multiplying the y coordinates, right? The y is our f of x. The y coordinates of each point on the graph of my original f of x equation by a, and leaving the x coordinate unchanged. The result is a, this is our first example, we see a vertical stretch away from the x-axis if I have a value that's more than 1, right? So our 2 there doubled every value. So if I multiplied by 4, that would quadruple every value, etc. It would stretch it even further upward. And it becomes a compression toward the x-axis if my value a is somewhere between 0 and 1. Of course, if I multiply by 1, it remains the same. If I were multiplied by 0, I would have no graph. Every input would get multiplied by 0 and would just become 0. Here's a generalized picture of what we're talking about here. So if a is less than 0, so it's negative, first graph, y equal to the absolute value of a times f of x by stretching it or compressing the graph of it vertically. Then we would reflect the graph across the x-axis. All right, we're going to see on the next slide that idea here. So here we have our original graph, and a here is more than 1. So that's going to stretch it vertically. So for every input, we had our output, our original graph. But what we see is that in the new graph, the graph that is a times the original, each y value gets multiplied by a. And so that stretches it upward. And if you're down here, it's going to stretch it downward. So basically, it's almost like taffy pulling it up and down. And if it's a fractional value, it's going to compress it vertically. So we have kind of it's moving it toward the x-axis, where here it's moving it away, stretching it away from the x-axis versus compressing it toward the x-axis. That's when the a value here that I'm multiplying is a fractional value that's less than 1, greater than 0. Great. Let's look at one last example here that we can apply all these to. Here's our function. Our function is a parabola because we have something being squared, but we've subtracted 1 from the x, we've added 3, and then we've multiplied it by not only just a 2, but a negative. So it seems like we've thrown almost everything into this particular one. All right. I don't have white, so actually I do. I think I can, I can go with a white, which will be appropriate here. I just had to change the black to a white. But, okay, so let's write out what we have going on here. My original equation, of course, is x squared. So here's my original equation. Usually we're calling that f, but we'll call it g in this case. My original equation, g, is x squared. This is an x squared function. We're adding and we're subtracting to it. We're multiplying by negatives. But when it comes down to it, it's just going to be, as we know, a quadratic equation. A parabola, right? So if I were to graph that out, and we're going to need something other than white over here, let's put it in blue. We have 0 squared is 0, 1 squared is 1, negative 1 squared is 1, 2 squared is 4, negative 2 squared is 4, 3 takes us up to 9, but which is off of the charts here. Okay, but this gives us kind of a visual of our original function. And there we have it. Now, I do this because I want to be able to graph some points for my new function, but I need to look at where my vertex is going to be, where this guy is going to be. And then I'm going to pick points that are around that x value, right? Because x's are what we're plugging into our function. So looking at what we have here, we have a subtraction of 1 to start off with. And it's with the x. So this is a horizontal result, and it's going to move it to the right 1 unit. Right? When we do stuff to the x, it shifts it horizontally, and it does it in the opposite direction. And then our addition of 3 means it's going to shift up 3 units. So taking what I have here, we're going to put this one in red. I know it should shift the vertex of my parabola to the right 1, and it's going to shift it up 3 units. So my new vertex is going to be here, right? So for the x value of that being at 1, I'm going to put 1 here, and then we know 3 is the result. I want to pick points around 1. So if I go 1 to the left of 1, I'm at 0, so 0 is going to be one of my numbers that I put in. And then I'm also going to go another one to the left, so negative 1. And then we're going to go from there to the right. So to the right of 1 is 2. So we're going to plot in 2. And then 1 more to the right, 3. Notice that I'm not adding, I'm only going by ones. That's because when I square something, it becomes much, much larger, much, much quicker. So we just got to be careful in that way. So that's the shifts. And then I also know that we have this multiplication by negative 2. So the negative I know is going to flip the original equation, right? So now we're going to have a downward facing parabola, and it's going to stretch it by 2 units. Stretch vertically by 2 units. Okay, well that's good to know. That's just kind of our expectation that I'm going to have a downward facing parabola that is stretched downward. So it's not going to, it's going to be less of a U, right? It's going to be a steeper lines there. And now it's a matter of plugging these in. I want to actually plot out our original, okay. I'm not going to use my original points because we've shifted it, so that messes them up. We're just going to plug these in. I'm going to find the f of 0, which is negative 2 times 0 minus 1 squared plus 3. So doing this first, we complete that. This is negative 1 squared. And negative 1 squared is positive 1. So now I have negative 2 times positive 1. I carried out the square first. Then I do my multiplications, which by negative 2, so that's negative 2 plus 3. Negative 2 times 1 is negative 2. And negative 2 plus 3 is positive 1. So 0, or no, what did I plug in there? Yes, I plugged in 0. 0 gives me 1 as a result. So I'm assuming 2 is going to do the same thing. What happens with 2 in there? Well, 2 minus 1 is positive 1. Positive 1 squared is still positive 1. Times negative 2 is negative 2, so we still end up getting positive 1 as well. So I established that if I move the same direction away, the same amount in either direction, subtract 1 and add 1 to 1, I get the same y result. So 0, 1 and 2, 1 are points on my parabola. And now let's go to negative 1. And with that, I'm going to start over here. Just because I've got limited space. So again, now we're going to go f of negative 1. Negative 2 times negative 1 minus 1 squared plus 3. So this is what I substituted in there. Let's do the parentheses first. Substitute, or not substitute, but simplify what's in there. Negative 1 minus 1 is the same as negative 1 plus negative 1, which is negative 2 squared. Notice that I'm just taking it one step at a time. It's because I don't want to mess this up. That means I have to go back and fix it later on. So the more steps I'm taking, the better. Negative 2 squared is 4. And so that's 4 times negative 2 plus 3. Well, negative 2 times 4 is negative 8, which results in negative 5. So I got negative 5 here when I substituted negative 1. I've already established the symmetry. Negative 1 is 2 units away from positive 1, and 3 is 2 units to the right of positive 1. So I can assume I'm going to get the same thing here. Going back and just looking, you can double check it. You don't necessarily have to, but 3 plus negative 1 is positive 2. So you can see that that's how we end up with the same numbers. So negative 1 and negative 5, and way down here, positive 3 also gave me negative 5. All right. So what we see is, yes, a parabola that's upside down. Isn't that great when we have these expectations and then we see them actually get carried out, right, in our calculations and then confirmed also with our graphs. So there's my parabola. It took my original parabola, flipped it upside down, stretched it, and then moved it to the right one and up 3. Well, the vertex. And each point really got stretched, but the vertex is really unchanged in terms of its position because it's a 0, right? And a 0 result doesn't matter what you multiply it by. So the long and the short of this is we want to think about what is being done to my equation, right? What kind of transformations took place by looking at what we did to the x before we squared it or took the absolute value of it or took the square root of it or what have you. We always do something to the x that's significant, that makes it the type of equation that it is. So whatever we do to the x, we look at the addition or subtraction of it, and that shifts it in the opposite direction. If we add 1, it moves it to the left. If we subtract 1, it moves it to the right. Whatever we do to the overall equation, right, after we've squared it, if we add stuff or subtract it, moves it up or down in the same direction as a sign. And if we multiply it it stretches it up or down. If it's a negative that we're multiplying, it actually flips it, and then we'll stretch it, or maybe it doesn't if it's just a negative one. Once you've established what you did, find the vertex, or kind of that centering point, or starting point, like we had with the square root function. We had that starting point, and then use that as a way to decide what x values you want to substitute, so you can get some specific points to graph your equation. That completes this particular thing of transformation of functions. Remember to practice graphing these things out on your paper. It's important because you want to be able to do that when I have you actually do it on paper, right? Find that centering point. Here our centering point was the 1, 3. That was our vertex. And then from that, we subtract and add the same values in either direction to give us that symmetry, if that's what we're after, if it's like the V or the parabola or something that's symmetric. And just use that as some smart ways to start to decide what values for x you want to plug in, and then plug away and see if it confirms what you were suspecting. And if it doesn't, then something's off. So you got to go back and go, wait, did I misinterpret what direction I should have moved? Thanks for paying attention, and good luck as you start applying these principles on your homework.